All right, so now for objective 3, we want to solve trigonometric equations quadratic in form. So we can also solve trigonometric equations by using the quadratic equation or just by factoring. So example 4, we want to solve 2 cosine squared of theta minus 3 cosine theta plus 1 is equal to 0, where theta is in between 0 and 2 pi. So if we look at this equation, we know that we can always use the quadratic equation. But factoring is a lot easier and it's a lot cleaner. So we want to always see if we can use factoring. So if we want to use factoring, we see our first item here is cosine squared of theta. It has a 2 in front of it. Our middle term is a negative 3 cosine of theta, and our last term is a positive 1. So this means that if we can factor, then our equations are most likely going to end up looking like 2 cosine of theta, cosine of theta, and 1s. Since we know that positive 1 and positive 1 have to multiply to be positive 1 or negative and negative 1. So, considering that our middle term is negative, it would make a lot more sense if our middle term was negative. This means that when we go ahead and we FOIL out our equation, we would end up with 2 cosine of theta times cosine of theta, giving us 2 cosine squared of theta. 2 cosine of theta times negative 1 would be negative 2 cosine of theta. Negative 1 times cosine of theta would be negative cosine of theta. And negative 1 times negative 1 is positive 1. This ends up giving us our value, which means that our equation was factorable. So since our equation was factorable, and we now have two equations here that are set equal to 0, we can go ahead and we can separate them out. This means that either one or both can be equal to 0. So this means that 2 cosine of theta minus 1 is equal to 0, and cosine of theta minus 1 is equal to 0. So we can go ahead and we can solve for cosines of theta. So starting with our equation here on the left, 2 cosine of theta minus 1 is equal to 0. We add 1 to both sides to get 2 cosine of theta is equal to 1. And then we divide by 2 on both sides to get cosine of theta is equal to 1/2. Then on our right side, we have cosine of theta minus 1 is equal to 0. We add 1 to both sides to get cosine of theta is equal to 1. So we now have these values. We can take the inverse trig function if we wanted of both of these cases, or we can just think about what values of theta give us cosine of theta is equal to 1/2 and cosine of theta is equal to 1. And then we can find those solutions. So in the case of cosine of theta equaling 1/2, theta can be either pi over 3 or 5 pi over 3. Then for cosine of theta equal to 1, the only value of theta that would give us this would be 0. Technically also 2 pi, but since they're almost the same, we don't actually consider 2 pi, we only consider 0. So I've now found 3 solutions of theta for our equation. So we get then on the interval, (0 to 2 pi, not including 2 pi, we have the solution set, is going to be equal to 0, pi over 3, and 5 pi over 3. And there we have our solution set. If you had to use the quadratic formula, it would end up being the same thing where whatever answers you finally had in your quadratic formula, you would set those equal to 0 as well and find those values. Then our last objective, we want to solve trigonometric equations using fundamental identities. So fundamental identities, remember we learned this back in chapter 6. So we can also use fundamental identities to help solve trigonometric equations. So in example 5, we want to solve cosine squared of theta plus sine of theta is equal to 2 for theta being between 0 and 2 pi. So we always want to try and factor first, but I'm going to save everyone time and just say that this can't be factored. So we're going to start off by saying that. This cannot be solved by factoring. Factoring. So it can't be solved by factoring, but we can use other ways in solving it. It also can't be solved by using the quadratic formula, and this is because if we use the quadratic formula, we end up with a negative number under our square root, which then would just mean that it was undefined. So we say that this can't be solved by factoring or by using the quadratic formula. So we have to use identities. So if we go ahead and use identities, we have cosine squared of theta plus sine of theta is equal to 2. We can replace cosine squared of theta pretty easily. We know that cosine squared of theta is equal to 1 minus sine squared of theta. So if we replace this, we end up getting 1 minus sine squared of theta plus sine of theta is equal to 2. So now we can try and simplify this and solve for sine of theta. So now that we have this, we can simplify a little bit here. So if we go ahead and we subtract 1 from both sides, this would end up giving us a negative sine squared theta plus sine of theta is equal to 1, since we subtracted that 1 from both sides. Then we don't want a negative sine squared of theta as our first term. We want it to be positive, so we're going to multiply it by negative 1. So let's kind of write this out. First, we subtracted 1, or here. Subtract 1. Then we're going to get sine squared of theta minus sine of theta is equal to negative 1. And we multiplied by negative 1. Now we want to have an expression equal to 0, or we want to have an equation where our equation is set equal to 0. So we're going to go ahead and we're going to add the negative 1 to both sides. So this gives us sine squared of theta minus sine of theta, plus 1 is equal to 0. So we added 1. And now we have an equation that is equal to 0. It's not equal to 2 anymore. We also only have one single trigonometric function, and it is still not factorable. This is still not factorable.
I know, why not number 6?
Even with what we have here, we can't factor it out evenly. And once again, if we use the quadratic formula, it would end up giving us a negative value under our square root, which means that it is undefined. So This is also still not factorable. This means that this solution, or sorry, this equation is going to have no real solution. So the solution that we give is going to be called the empty set. If we find that an equation has no solution and we want to write that it has no solution, we give it the empty set, which is a circle with a backslash through it. We do not write it in curly braces like how we would end up writing a solution set. We just write the empty set in this way. So there is one more objective in this section, but you can go to it if you would like to see about it. The section just goes over how to solve these problems using specifically a physical graphing calculator. It's not helpful if you have Desmos or if you have a calculator that doesn't have graphing capabilities. If you do have a physical graphing calculator, then by all means you can go and look over Objective 5, and it goes over how to use it and also how to solve problems like this using those graphing features. So if that applies to you and you would like to go through that, by all means, you can go through that as well. And then it would just be one other kind of way that you could go ahead and solve these problems on your own. So all right, that finishes up our section 7.3. So I'll see you all again in section 7.4.